Welcome back. In the previous lecture, we have talked about sampling process. Our whole PCM system was consisted of three basic parts. They were sampling, quantization, and encoding. So as we have completed our discussion on sampling, we will start talking about quantization today. So sampling was basically discretizing the signal in time domain or time axis, and quantization is discretizing the signal in y-axis or in amplitude. So let's see how it is done. A basic signal is shown here to demonstrate the sampling and quantization process together. So let's say this is the signal, this black line here, this sine wave, and we are going to first sample it and then quantize it. Sampling means discretization in time. So at first we have to divide the whole time axis in several parts, and the distance between each part will be the same because we had a time interval which we call sampling interval. Here the sampling interval is t, so you can see the first instance is 0, and after t time the second sampling instance is at time t, the third sampling instance is at time 2t, and it goes on and on. That means is basically we will take a value from the signal after every t time. Let's say our first sample is taken at 0 time, so this is the sample. Our next sample is taken at t time. You can see the sample is denoted by this small white dot. At t time, the signal value is this small white dot. Then after another t time, that means at time 2t, the signal value is here, another white dot, and it goes on and on. This is the first step, the sampling process, discretization in time. After this discretization in time, we have to discretize the signal further in amplitude too. The similar process is followed in amplitude. To discretize the amplitude, at first we need to determine the signal range or the quantizer range. The quantizer range is basically the difference between the highest value of the signal and the lowest value of the signal. Here you can see this is the highest value of the signal and this is the lowest value of the signal. So this whole range is our quantization range or signal range. There's the same thing. We have to divide this quantization range in equal parts, just like we were doing in the sampling. So we have divided this full range into 8 parts. You can see first part, second part, third part, fourth part, fifth part, sixth part, seventh part, and 8th part. We have divided the whole range in 8 parts. And you can see these black horizontal lines, they all are called quantization levels. This black line is quantization level, this one is another quantization level, this one is another quantization level, this one is another quantization level, and so on. So we have 9 quantization levels here, which means we have 8 steps because there are 2 lines in 2 borders. So we have 9 quantization levels and 8 steps. Each of this range is called a quantization step. So we can adjust this quantization step according to our need, and we can increase the number of levels. Let's say if I just make the quantization step half, then my quantization level will be doubled, and if I set my quantization step to double of this delta, then my quantization level will be halved. That is how it is done. So at first we have to determine the signal range or the quantizer range, and then we have to divide the quantizer range into equal parts. Let's say our quantizer range is 10 and our quantization step is 2, then we will have total 5 steps, and 5 steps means 6 levels. That is how it is done. Another example, let's say our quantizer range is 14 and our quantization step is 1. That means we will have total range by quantization step. So 14 by 1 is 14. So we will have 14 steps, and 14 steps mean actually 15 levels. That is how it is done. So after discretizing the grid, then we will have to assign the values. Let's say our first sample was taken at 0 time and this was here. This sample already corresponds with the quantization level, so we do not need any further calculation. So the first value is 0. Then at time t, our signal value is somewhere here. So now we have to decide where do we want to quantize this sample. because now the y-axis is discretized and we can use only the values specified here. We cannot use anything between 3 delta and 4 delta. We have to use either 3 delta or 4 delta. We cannot use anything between 0 and delta. We have to use either 0 or delta. So now our signal value is somewhere in between 2 delta and 3 delta, but we cannot use anything in between. So we have to use either 2 delta for this or 3 delta for this. But from the naked eye view, it seems that this sample is somewhat closer to 3 delta. So we will quantize this value to 3 delta. Then at 2t time, our signal value is somewhere here. It is quite apparent that this sample is very close to 4 delta, so we will quantize it to 4 delta. Then again at 3t time, our signal value is here. So from the view of naked eye, we can again quantize it to 4 delta, but it seems in between, so we could quantize it in both the ways, in both 4 delta and 3 delta. The theme is we have to quantize a sample to the closest quantization level. This is the basic, and it is done all the way. Now you can see whenever we are quantizing this sample to 3 delta or this sample to 4 delta, an error is introduced because we are making an assumption on our sampling instances. So while quantization is done, an error is introduced. We will analyze this error in the later sections, but to give a heads up, we have an error. Okay, so some notations. XAT is the original analog signal, and the unquantized samples are called XANT. I have explained this in my previous lecture, why there is an NT in between. XAT is a function, and we are taking the samples from the original signal at t time intervals. Depending on the value of n, we can get 0 here, we can get t here, 2t here. That's why it is called XANT. And when we are quantizing it, this becomes XQNT. Obviously, this is NT because we are not changing the time interval, so this is NT. But as this is quantized now, we are giving a underscript Q. We are done with quantization. Another thing, for this example, we are quantizing using a method where we are quantizing a sample to its closest value. There are two types of quantization basically. The first one is rounding and the second one is truncation. The scheme we are following is called rounding. There is another scheme that is truncation. What is truncation? Let's say this sample is between 2 delta and 3 delta. So we will always quantize this sample to 2 delta, or we are quantizing a sample to the lowest quantization level, not the higher one. So for this sample, it is between 3 delta and 4 delta. So obviously in truncation method, we will quantize it to 3 delta. However close it is to 4 delta, it doesn't matter. For this sample, we will quantize it to 3 delta. For this sample, we will quantize it to delta because we are using truncation, and so on. So this was our quantization process. I hope you have got a good overview of it. Now let's move on and see what's up next. Okay, so in this slide, quantization process is described somewhat mathematically. Let's say we have a continuous sample M. What is continuous sample? Continuous sample means after sampling a signal, we have taken some samples from the original signal, and those were continuous in amplitude. There were no restriction that this amplitude cannot be 5, cannot be 10, no restriction. That is what we are calling continuous sample M. We are going to pass it through a quantizer and we will get our discrete sample V. This G is our quantizer function. We are inputting M in it. This is continuous sample. By continuous sample, I mean is this white dot. This is a continuous sample. When we are passing it through a quantizer, we are getting this V. V is the black dot here. That is the quantized sample or the discretized sample. So we are already aware about two type of quantization schemes. They are rounding and truncation. Let's see how it is done. Okay. So let's say this was our y-axis. We are putting it horizontally now, but let's say this was our y-axis. Our first task was to divide this y-axis in equal parts or equal segments. Let's say this is our first level, this is the second level, this is the third level, this is the fourth level. You can see the distance between these levels are same. The distance between mk minus 1 and mk, and also mk and mk plus 1 is same. And this interval is called ik. Ik is the quantization step. as we all know. These MKs are called decision levels or decision thresholds. Now we will put another level in between two MKs. Let's say here is MK and MK plus 1. We will place another level VK which is bisecting these two levels. We will put another level VK plus 1 which will bisect these two levels. We will put another VK minus 1 which will bisect these two levels. These VKs are called representation levels or quantization levels. Now, why do we need both MK and VK? Let's get back to the previous image. Let's say this sample here, we want to decide whether to quantize it to 3 delta or 2 delta. From the naked eye view, we can already assume that this is somewhat closer to 3 delta. So in rounding method, we are going to quantize it to 3 delta. That's fine. That's the view of our eye. But what's the scientific process behind that? What we do is, we further divide each quantization step in two parts. Let's say there is somewhat 2.5 delta somewhere here, and 3.5 delta somewhere here, and 1.5 delta somewhere here. By common sense, when we will quantize a signal to 2 delta, if it is closer to 2 delta, right, it can be somewhat larger than 2 delta or somewhat smaller than 2 delta. But the theme is, if that sample is closer to 2 delta rather than 3 delta or delta, then we will quantize it to 2 delta. So that signal may be greater than 2 delta or less than 2 delta. So we should have a range such that if a sample is in that range, we will quantize it to 2 delta. How we can do that? We can imagine a 2.5 delta here and a 1.5 delta here. So if a sample is between 1.5 delta to 2.5 delta, we can safely quantize it to 2 delta. Another example, let's say this sample, we are quantizing it to 4 delta, that's fine, because from the naked eye view it is closer to 4 delta. But what's the mathematics behind that? Let's say we are assuming two further divisions. One is at 3.5 delta, another one is at 4.5 delta. If a sample is falling between 3.5 delta or 4.5 delta, then we will quantize it to 4 delta. Let's say our sample value is 3.7 delta. Obviously 3.7 delta is greater than 3.5 delta and less than 4.5 delta, so we will quantize it to 4 delta. But if this sample was 3.3 delta, then it was not greater than 3.5, rather it was less than 3.5, and we would quantize it to 3 delta then. These levels are called quantization levels, and the further levels we are dividing or creating in between these two levels are called decision levels, because they help us to take decision. Let's say we are quantizing it to 4 delta. Why? Because it is in between 3.5 delta and 4.5 delta. So those 3.5 delta and 4.5 delta are not helping in quantization, but they are helping in decision making. That's why these aims are decision making intervals or decision levels. And when a sample is falling between consecutive decision levels, we are going to quantize that sample to the quantization level in between them. Let's say this was our 3.5 delta and this was our 4.5 delta, the decision levels, and we have a quantization level 4 delta in between. So if a sample falls between 3.5 delta and 4.5 delta, we will quantize it to 4 delta by rounding method. So MK is decision levels or decision thresholds, and VKs are representation levels or quantization levels. One obvious thing is the difference between two consecutive decision levels or two consecutive quantization levels are always equal, and this is called delta or step size. Okay. What is rounding? Rounding is a sample M which is continuous when is given input to a rounding quantizer. Then first the rounding quantizer checks which two decision levels does the sample lies in between, and then accordingly it provides a quantization level to it. Let's say IK is the kth interval, and IK means the difference between MK and MK plus 1. So if a sample lies between mk and mk plus 1, or in other words, if a sample lies between this ik, then we will quantize it to vk. You can see here, v is equal to vk, v is quantized sample, if our non-quantized sample or the continuous sample m lies between ik. Let's say this is ik plus 1. So if our continuous sample lied between ik plus 1, we would quantize it to vk plus 1. That's what rounding is. And truncation is very straightforward. Let's say this is our vk and we have a vk plus 1 here. In rounding, the decisions are taken by different levels and quantization levels. But in truncation, the decision levels and quantization levels are same. We don't need any extra decision levels because the quantization levels are suggesting where to quantize. Let's say our quantization levels are at delta, 2 delta, 3 delta, 4 delta. A signal or a sample is lying between delta and 2 delta. Then we will always quantize it to delta. If it is even 1.9 delta or 1.99 delta, however close it was to 2 delta, that doesn't matter. As long as it is between delta and 2 delta, we will always quantize it to delta. That is what truncation is. So moving on, there are two types of quantizations, mid-trade and mid-rise. Detail of these quantizers or these graphs are not required. The thing that is important here is, when we are using truncation, our task is to set both decision levels and quantization levels. So, in the case of mid-trade quantizer, we put a quantization level or a reconstruction level at 0 value or exactly 0. You can see a sine wave, it goes up from 0 and then comes down below 0. It has a range. 0 is somewhat in between of that range. And for mid-trade quantizer, we always set a representation level or a quantization level at 0, and then we make other quantization levels and decision levels. Let's say our quantization step is delta. Then if we set a reconstruction level to 0, then our another reconstruction or quantization level will be at delta, another one at 2 delta, 3 delta, and in the negative side minus delta, minus 2 delta, minus 3 delta. So something like this. So this is our mid-trade quantizer because we are having a quantization level at exactly 0. It would be a mid-rise quantizer if this 0 was not a quantization level but a decision level. For this original quantizer, we are having a quantization level at 0 and decision level at 0.5 delta, minus 0.5 delta, 1.5 delta, 2.5 delta, and so on. But if this 0 itself was a decision level, this delta was a decision level, this 2 delta was a decision level, then we would call this quantizer a mid-rise quantizer. And in the case of mid-rise quantizer, we would have reconstruction levels or quantization levels between these two decision levels, or 0.5 delta would be a quantization level, 1.5 delta would be a quantization level, and so on. So this is the difference between mid-trade and mid-rise quantizer. We don't need any detail or the graphs here. We just need the idea that for the mid-trade quantizer, we have a reconstruction level or a quantization level at exactly 0, and we have a decision level at 0 for mid-rise quantizer. So that's all for this lecture. We will talk in detail more about quantization and other aspects of quantization in our next lectures. Thank you.